plus x squared plus 5x plus 1. With the use of graphing calculators, all this stuff with Descartes' rule of signs, rational theorem, kind of is not as important as it used to be for finding zeros. But this graph shows that there's two roots right here that kind of look like, well, maybe there's only one root, but there's, when you look close, you see that there's two roots here. And the four roots of this rational, or of this polynomial function, are negative 1/2, 2 plus the square root of 3, 2 minus the square root of 3, and 1/4. The question is, how could you find those roots without a graphing calculator? Could you do it? Well, so the answer to this first question, the maximum possible numbers of possible positive and negative roots, is found by using Descartes' rule of signs. And what that says, well, this should be x. The number of sign changes, as long as we have real coefficients, the non-zero constant term, we can apply part 1 here. The number of sign changes is positive to negative is 1, negative to positive is 2, and positive to negative is 3. So there's either 3 real zeros, or we count down by an even number. So there's either 3 or 1 positive real zeros. If we take b of negative x, that just means where all the exponents are odd, the sign of the coefficient of that term is going to change. So we'll have 6x to the 4th plus 23x plus x squared and minus 5x. And then if you count the sign changes, there's only one. We go from this positive to negative. So there's possibly one negative real zero. If it turns out it's a 1 and 1, that means there will be two complex non-real zeros. That is, they're form a plus bi. Okay, so remember those numbers: 3 or 1 positive real zeros, possibly 1 negative. Now, if we're going to use the rational root theorem to use the rational roots, and I can write back on I should probably say rational roots, not integer roots, and non-rational roots. Anyway, the rational root theorem says says that if we have a rational root, then the numerator of that rational root, like the rational root C must be a factor of the constant term, and D must be the factor of the leading coefficient. So here's the constant term. So the numerator has to be a factor of plus or minus 1. Let's use plus or minus 1. The denominator has to be a factor of 6. There's the factors of 6. Plus or minus 1, 6. So the possible rational roots are plus or minus 1, plus or minus 1, plus or minus 1, plus or minus 1/6. We can test f of plus or minus 1 directly instead of using synthetic division. But like 1 and we see that we get a number that's not 0, and f of negative 1 not 0, so we can rule these out. Now we might try plus 1/2 synthetic division, off the 6, multiplying that, we see 1/2 does not give. Applying 1 again for 0 here, so that's out. We try negative 1/2, and we can remain 0, so negative 1/2 is the one negative root. That's it. Now we don't have to try any of the negatives. Let's try a positive. 1/3. Wow, we stumbled right away. So -1/2 is one rational root and 1/3 is another rational. So that means that the original function is plus a half times the third. And here's the residual function from which I can factor out a 6. And then I do it this way. So I'm going to find the roots of this back to 0. I can use the quadratic formula. And A is 1, B is 4, C is 1, it's plus or minus 2. So that, there they are, 1, 2, positive root, and these are both positive. There's 3, so there are no complex non-real roots, nothing in the form of plus b minus 1. And on the third board, I meant to do this as our second step here. But there's this theorem that says that if you have a polynomial with real coefficients, all the zeros are in the zero. Negative m or m is whatever this is. Well, we want the maximum coefficient in absolute value divided by the leading coefficient. And then add 1. And that turns out to be 4 and 5 and 6 for m. So all the zeros are within this group. And all of our potential rational zeros by the rational theorem or in that interval. So it makes sense to test all of those. And even the 2 plus or minus the square root of 3. Go back to this board. Those values are 3.732, 2.267, which are definitely less than 4.6. So there you go. Hope that helped. If you have any questions.